Hi, we are still working on integrating powers of trigonometric functions. In this video, we are going to examine case 4, even powers of secant. The methods we will discuss in this video should only be used if you've verified that the integral is not basic, that substitution and IBP fail, as well as algebraic methods. Even powers of secant can easily be recognized by secants whose powers are even, either on their own or combined with tangents. So how does this method work? We're going to examine secant x to the power 6 as a guiding example. In step 1, factor out a secant square x term and associate it to the dx. This combination of secant square x and dx is meant to become du later on. In our example, secant x to the power 6 has become secant to the power 4 with the secant square x that we have pulled to the side with the dx. In step 2, use the identity tan square x plus 1 equals secant square x to replace all the remaining secant square x's. By remaining secant square x's, I mean all those that we have not pulled aside along with the dx. In our example, that means that we have to replace secant x to the power 4, and in order to do so, we will break it up into secant square x's that are squared first, and then proceed with the replacement. Now remember that the derivative of tan of x is secant square x. And therefore, in step 3, we will apply the substitution u equals tan of x, which fits perfectly with a du of secant square x dx. Therefore, by the time our substitution is completed, we only have powers of u left. In step 4, complete the antiderivative by using expansion or splitting the denominator and return to variable x. In our case, expansion is necessary in order to get individual powers of u. And lastly, the power rule can be applied to complete the antiderivative process. Finally, every u stands for tan of x, which is our way back to our original variable. If we are discussing a definite integral, then bounds can be replaced as you apply the substitution. For example, here we have secant x to the power 4, an even power of secant that is accompanied by a tangent, as well as bounds. Our first step, as seen previously, was to pull out a secant square x term to go along with the dx. The leftover terms of secant square x were replaced by using the trig identity tan square x plus 1. Once again, if u is to replace tan of x, du would be secant square x dx, which is waiting on the right-hand side. And therefore, that's what we'll choose to do. Let u become tan of x with du equals secant square x's. As this integral has bounds, we will adapt the bounds along with the u that we've chosen. The bottom bound, pi over 4, has a corresponding value for u, which is tan of pi over 4, which is 1. The upper bound, pi over 3, has a corresponding value for u, which is tan of pi over 3, which is root of 3. And therefore, our integral in terms of u is a combination of powers with new bounds for u themselves. The antidifferentiation process can be completed by splitting the numerator and by applying the power rule to the first term and recognizing the second is a logarithm. In our final step, the bounds are replaced by using FTC part 2, which leads to 1 plus tan ln of root of 3.